Let A be an n by n matrix. A is said to be symmetric if A is equal to A transpose. For example, these are all symmetric matrices. Symmetric matrices are found in many applications, such as control theory, statistical analysis, and optimization. There are two important properties satisfied by real symmetric matrices. The first is that such matrices have only real eigenvalues. The proof of this requires a bit of ingenuity, but the 2x2 case is rather straightforward. The second property is that every real symmetric matrix is diagonalizable. In fact, we can say a bit more. So, if A is a real symmetric matrix, then A can be written as U times D times U transpose for some diagonal matrix D and some matrix U satisfying U transpose equals U inverse. A real square matrix that satisfies this is called orthogonal. And if a matrix can be written like this, then it's said to be orthogonally diagonalizable. The proof of this result is rather tricky. Here we'll prove the result for the case when the eigenvalues are distinct. First, let's establish the following result. If A is a real symmetric matrix, and U and V are eigenvectors of A with distinct eigenvalues lambda and gamma respectively, then U transpose times V is equal to 0. Or equivalently, U and V are orthogonal. To see this, let's look at lambda times U transpose times V. This can be rewritten as lambda times U transpose times V. But lambda times U is equal to A times U because U is an eigenvector of A with lambda as eigenvalue. So this can be rewritten as A times U transpose times V. And expanding the transpose, we have U transpose times A transpose times V. But A transpose is the same as A because A is symmetric. So this is the same as U transpose times A times V. And now A times V is gamma times V. And so this is equal to gamma times U transpose times V. And so I have established that lambda times U transpose times V is the same as gamma times U transpose times V. And if U transpose times V is non-zero, then lambda is equal to gamma, which is a contradiction. And so U transpose times V must be 0. Now let's take A to be a symmetric n by n matrix with real entries. And suppose that it has the eigenvalues lambda 1 to lambda n all distinct. Remember we stated earlier that real symmetric matrices have only real eigenvalues, so all these are real. And since there are exactly n eigenvalues, each eigenspace is spanned by a single vector, and we'll call that vector ui for the eigenvalue lambda I. Because the eigenvalue is real and the matrix A is real, these ui's are real. And we are going to assume that each ui is a unit vector. If not, we can replace ui by 1 over the norm of ui times ui. This step here is called normalization. And so if we let U to be the n by n matrix with columns u1 up to un, and D be the diagonal matrix with lambda 1 up to lambda n on the diagonal and zeros everywhere else, then we can write A as U times D times U inverse. In order to complete the proof, we have to show that U inverse here is the same as U transpose. Let us now look at the product U transpose times U. If you look at the ij entry of this product, it's given by row I of U transpose times column j of U. But row I of U transpose is precisely column I of U transpose. And so we can write this as Ui transpose times Uj. But this is 0 if I is not equal to j, because Ui and Uj are eigenvectors of A with different eigenvalues, and we are using this result here. And it's 1 if I is equal to j, because if I is equal to j, I'm just taking ui transpose times ui. And because ui is a unit vector, ui transpose times ui, which is the square of the norm of the vector ui, is 1. And what this gives us is that u transpose times u is the same as the n by n identity matrix. So what this proof shows here is that in the case when the eigenvalues are distinct, you simply follow the procedure for diagonalizing A, and then you just normalize each eigenvector. The resulting product that you get here will give you orthogonal diagonalization of A, because U inverse will be equal to U transpose. We'll see an example of this in the next video.